Okay, let's take what you've been learning in circuits so far and bring that into the way that we're going to be looking at it in computational multiphysics. So the idea with this is you've been learning so far that current is equal to 1 over R times V, right? So this is current, which is equal to 1 over the resistance times your voltage difference. It's going to be a little bit hard to see. Let me try and bring another marker here. Okay. Now, first of all, if you're paying attention, you'll realize that this V isn't the voltage, it's the voltage difference. Okay. So it's actually better written as 1 over R delta V. And the idea here is that if we have our one-dimensional domain, we have a voltage, which is here on one side, down here on the other side. This is the difference as it goes across that 1D. So this is a wire, effectively. Okay. Now, what you want to do is consider breaking down this one-dimensional wire into a continuum. And over each of these continuums, you have delta V, delta V, delta V. I'm sure you can't, I don't know if you can actually read that out. But what we're going to do is we're going to shrink that down and make it smaller and smaller and smaller. Going to reach into our calculus toolboxes as delta V over delta X, this is X here, goes to, as delta X goes to 0, of course, this becomes the derivative of V with respect to X. Okay? So when you move that over to your equation, what you're going to find is at any point here, we're going to have 1 over R di V by di X. Okay, first things first. There's a little foible in all this that the current is usually talking about the movement of a negative charge. Right? This is a little bit confusing because generally speaking, we like to talk about positive things. So a positive charge moves the exact opposite direction of a negative charge. Let's write that as a new variable. Let's call it J, our current density of positive charges. This is going to be 1 over R negative di V by di X. And why I want you to think about it that way is because this is now pretty intuitive. What this is saying is that the current, the movement of positive charges, is flowing down the gradient. So, down the slope. So if you have a voltage that looks like that, which way is the current going? Well, it's going down the slope. It's literally falling downhill. Now, when we talk about multiple dimensions, instead of having this 1D, we're going to talk about it as, say, a square, 2 dimensions. Now we're going to have a voltage here, 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 everywhere along here. Which way at any given point is the current moving? Turns out it is exactly analogous in multiple dimensions. But now, instead of just saying di V by di X, we need the 2-dimensional analogy, which is called the gradient. And the gradient is quite literally di V by di X, this is as a vector, di V by di Y. And this is equal to grad of V. What the gradient is telling you, this is a review, is at any given point, it's going to show the magnitude of the maximum rate of change and its direction. Okay? So the way to think about this is if you're on a hill and the slope of the hill is going up like that, the gradient is going to be in the maximum uphill direction. Now, if you are on a hill and your slope is going most up that way and you lose your balance, which way are you going to fall? Are you going to fall uphill? No. Are you going to fall to the side? No. Are you going to fall downwards? Obviously. Okay? So the whole idea with this equation is now saying that your flow, your movement, your flux, movement of person on hill is proportional to negative of your gradient. Exactly the same thing with charge. It's going to be flowing downhill. Now, generally, if you're on a hill and you're about to fall, you're not just going to free fall like a rag doll. You're going to be fighting it. You're going to be pulling it back, hence the proportionality constant here. So generally what you would write, and I have to be careful not to go off the camera here, is instead of that, you would write out what your proportionality constant is. Let's call that the conductivity, because I am conducting myself down the hill. That's a poor analogy, I'm sorry. Okay. This is going to be negative sigma di V. Sigma is basically 1 over resistivity, because you're resisting falling down the hill, right? There's There's a lot of analogies here. Some of the words are actually well thought out. Do be a little bit careful with that because that also has implications about the cross-sectional area. So this isn't an exact one. You have to divide by the area too. Okay, so I'm not going to put that there. This idea of the flux going down the hill and being proportional to the speed going down the hill is very, very common, right? So if we have stuff like, for example, heat flux, okay? Our Q, which way is the heat going to flow? Is it going to flow from the cold to the hot? No. Is it going to flow from the cold to the cold? No. It's going to flow down the temperature gradient. Okay, so Q, our heat flux, is going to be negative grad T, right? Which way is our concentration going to flow? Is it going to flow towards more of the stuff? No, it's going to flow down the concentration gradient. So this is going to go negative grad C. I mentioned before that in my opinion, this is more appropriately mu. In linear phenomenological theory, which I don't think we're going to get to in this class, that's what it's going to be, but you don't have to worry about that right now, okay? This is good enough. Now, one quick caveat is that I'm being lazy here because the gradient is directional, right? If we're on the surface of a mountain, we need to know which way is downhill. As soon as we say which way, we're talking about vectors, right? This is all vector calculus. So the gradient, when you take the gradient of a scalar potential, like electric potential, hence electric potential, guys, temperature potential is technically a potential, chemical potential, okay? These are vector quantities. So this is more correctly written denoting which direction this is actually, okay? Let me just peek at my notes here. Now, next part. At any given point, let's take a small section here, make it big. We'll embiggen it, okay? This is a big blow up of this particular region in space over here. At any given point, we're going to have a flux on one direction of charge of whatever we want going in. We're going to have a smaller amount going out. But because we're in 2 dimensions, we also have a flux going up and a smaller flux going out. So how are we going to figure out how much stuff is actually stored inside the volume? Well, again, it's pretty easy, right? Anybody who's ever counted coins and like knows the basics of money can understand this sort of thing. All you're going to do is you're going to take this term, which turns out to be the flux in the x direction. That's the worst J ever, right? Minus the flux in this direction. And the difference between the flux going up, which is Jy, and this flux going up. So the accumulation inside this box is going to be really simply delta Jx, plus delta Jy. Very straightforward. But now we're going to do our calculus trick again. We're going to shrink this down smaller and smaller and smaller. Take that derivative, we're going to take that difference, that delta, we're going to shrink it to infinitesimal size, and lo and behold, we're going to get our derivatives back again. So this becomes di Jx by di x plus di Jy by di y. And the way that we're going to write this is actually something called the divergence operator. So that's going to be delta. I have to be cognizant that I'm almost off the screen here. Delta dot J. I'm going to erase this, give myself a bit more space here. Okay, and actually I'm going to rewrite this over here. Delta dot J. Sorry, not delta J. Del. This is the del operator. Okay, J is a vector field. What this is, and the reason why we write it like this, is because this turns out to be di by di x, di by di y, times our J field. And our J field, if you come back here, right, turns out to be, let's write that down here, di by di x, di by di y, dot J is just negative sigma di by di x, di by di y on V. Okay, so this is what the divergence is. It's basically saying from your volume, you have a certain amount of stuff going out, you have a certain amount of stuff going in, and that difference turns out to be your accumulation into it, hence your conservation equation and your balance equation.